Hey everyone, my name's Rudy Hill, and I've been an FPGA engineer for the last 5 years. And today we're going to be talking about the Sense amplifier. I'm making this video because there's a lot of stuff online. Um, Everyone wants to think that they're a great engineer, and hopefully I can be one day and be able to explain everything in perfect detail. I'm kind of just a person that wants to get his job done, wants to understand the basics, and have the intuition to be able to dive into it deeper one day. So that's why I'm kind of making this video. I saw a lot of videos online, and none of them were that intuitive, or none of them were, yeah, I mean, none of them were really intuitive enough, or some of them were incomprehensible with AI voices or other strange voices. But really, what helped me, ironically enough, was AI. So, thank you, Claude, for kind of breaking it down. Even if the diagram I made wasn't perfectly accurate, it gave me time to kind of look at it and review it. Well, enough chit chat. I'm going to assume that you have some basic background to electrical engineering. You don't need to know anything crazy. Um, you just have to understand PMOS and NMOS and CMOS. So, we're gonna start here and say that we have a signal A, and what I meant by CMOS, that you should be able to identify this very basic structure here, right? So we have A going to this PMOS and going to this NMOS above, and we'll call this VDD or something. We could just say it's 1 volt or something, just to say that this is a logical one versus right here ground is a logical zero, right? So usually with CMOS, we have, the complementary metal oxide semiconductor. That's what MOS means. And again, not too important, but I'm already assuming that you know this. So this is an inverter, basically. So the output of this will be not A. So let's just have a simple truth table. If A is zero, then the output, we'll actually call this, oh, we'll call this C. So if A is zero, C is one. If A is one, C is zero, right? So it just inverts it. So this is the very basic intuition that we need, or building block, I should say, that we need to start building this sense amplifier. So in later on, this will become relevant, but we can kind of denote this as an inverter like that to say that this is A and that's C. Now, this is supposed to be like a triangle, but you get the point. Um, so let's just draw the sense amplifier, and I'll kind of explain some of the intuition. Um, so here is, let's just draw out, oops, um, it's a VDD. Um, Actually, maybe it's a good time to kind of talk about why we're even talking about sense amplifier. Why, maybe I should have brought it up at the beginning, but maybe if you're clicking on this video, it kind of you're probably looking up for a very specific purpose, which is DRAM. You're trying to figure out, okay, I see the sense amplifier all the time in DRAM, and how does this work, right? So usually the thing is you'll have some sort of you have like the cell line. Well, I don't know what to call that. We'll just call this we'll call that VA, and then we'll have a VREF or something. And then VA is, some sort of capacitor value that's not quite one, not halfway. We have this kind of VREF that's half of the total voltage. So let me just kind of be more clear about this. We'll keep the numbers simple. So like VA is 1 volt, which is pretty close in some memory chips. Then VREF will be half of that, so like half a volt. And we have that as a ref because, of course, VA could be 0 volts. Yeah, and if you want to know more about DRAM, there's plenty of other videos. Maybe I'll make a more comprehensive video about all this. But once again, this video is for people that already have like a basic need to be looking for this video. So that's kind of the idea, is that this is where we're coming from. More than we're going to be building a general sense amplifier, but I'm going to be talking about it from the perspective of this kind of DRAM situation where we have a reference point. It could either be kind of be more clear. Either it could be like it's kind of leaking, so it's maybe like zero point 0.9 volts, um, or it's zero point 0.1 volts. So, it's basically one and zero, but not quite. And so we have this VREF to kind of um, to resolve this voltage. So we're gonna be doing this by connecting inverters, right? So I'm gonna kind of do the more complicated version, and then we're just gonna kind of simplify to summarize in the end. So the idea is that, okay, we have this, we're gonna have an inverter here, right? Oops. We're gonna have this inverter here, just bear with me. And we're gonna have an inverter here. And we'll have some sort of, oops, we'll have some sort of enable. This one is not, oh, oops. So it's not too important. But this is the main structure. We have these two inverters, and we're gonna do something very special to connect VA. We're gonna call it VA. We'll call it a VA and VREF, kind of like we had here, to kind of make it more clear. But realistically, and kind of when we simplify it, I'll kind of show you as like VA and VB generally. But let's just say we have VA coming in. Um, we're gonna connect VA in a very special way. So we're gonna have VA actually be the output. So if you remember up here, um, the output, that's not what I wanted. Uh, sure, blue's fine. The output of a CMOS is kind of in between the PMOS and the NMOS. So, you can kind of check that once we have the enable, if that's true. The enable is just kind of to turn on this device, but it's not really that important. Um, so yeah, this is VA is going to be the output of this inversion. But interestingly enough, what we're going to do is we're also going to have it be, oops, we are, let's see, where is, okay, here we go. We're also going to have it be the input to these gates. So it's going to be driving this inverter. Okay, fair enough. So let's deal with VREF. We're gonna do the same thing, but in the opposite direction. So we're gonna have it go to the output of this inverter that's being driven by VA. And so we're gonna hop over that and connect it to the gate here, hop over that, go into the gate there. So we're kind of, what we're doing from a high level is that we're feeding the output of one inverter to VREF, and we're using that as the input to the other inverter to VA. So let's think about this a little bit. So this is kind of what tripped me up of like what's actually happening. So let's look back at an inverter. There's a lot of, we'll say, deeper semiconductor stuff to consider. But let's just say, what if let's assume that A is, like I said, kind of this in between value of zero point 0.5 volts, um, as the gate, and we could there's a lot of things to say about saturation and triode or whatever. If you don't know that, you can look that up. But the intuition I'm going to bring here is that what is going to drive the output faster. A lower gate voltage, we'll call this could be like a VGS, right? This voltage on the gate. But is the output gonna go faster with a higher VGS or a lower VGS? With the higher VGS, current's gonna flow faster because presumably it's gonna be in triode or whatever. So we're just gonna kind of make a note of this. And kind of this is the intuition to go with that I'm kind of claiming here. A higher VGS means uh, a faster, uh, I don't know, faster logic, we'll say. Okay, so like I said, there's probably better math to describe this, and you can kind of prove it out yourself. But this is for people who are looking for like intuition first, and then you can kind of watch people that can show you the math and prove it out to you. But we'll say a lower VGS. No, and actually, really quick, I'm gonna step back and say this too. When I say higher, we're talking about more absolute. Like if it's zero, right, it's also gonna drive it faster too, because there's gonna be basically no output, or it's gonna be instant, right? Um, so it's gonna be like a harder drive. So maybe that makes sense. So really, I'm trying to figure out how I want to describe this, but pretty much what I'm trying to say is that, like, well, if you're stronger on one side versus another, um, if you have a solid one or zero relative to the specs of the transistor, that's really what I mean by um, up and down. Basically, it's the strength, the drive strength. So if you're like in this in between value at 0.5, it might be a one, but it's going to take a long time. So just go with me here. It'll be it'll become obvious. Or maybe not obvious, but it'll become kind of clear if you think about it. Okay, so here's the idea. So you have VA versus VREF. VA as the input to this, um, inverter right here. So this is kind of where VA is going. That's going to drive the output of the inverter faster than VREF pushing VA's inverter, right? So what's going to happen, this is kind of the sequence, is that VA, if it's a one, just assume it's a one, is going to drive the output, so VREF, to be zero, right? Because they're going to be opposite of each other since they're inverting each other. VA is going to win basically, um, because VREF is like in this weird in between. And if VA is zero, then VREF is going to be one. So this is what I mean by amplifying. So in the end, maybe they started out as, I use that example where um, VA is like 0.9 and VREF is um, VREF is 0.5 volts. So VA is like almost one or almost zero. Basically, it's going to have a stronger drive strength than 0.5. So it's going to win. This is kind of the general idea is that VA, if it is any closer to a one or a zero, and this is defined by VDD, of course. Um, if it's any closer to VDD than or ground, so basically closer to this or that. Oops, let's make that more clear. Then VREF, which is right in the middle, then it's going to win. And then, of course, once that is inverted, right? So once there's kind of this feedback, I'm kind of giving you these major passes, but if VREF, let's just say, is zero now from this first case, then I don't know if it's clear. Let's pick a different color. Uh, then we're going to follow that output here, and it's going to be the input to these gates. So what is that going to do? right? That's gonna reinforce, send feedback so that VA is more one, or it's just a feedback that we're talking about. And in the other case, when it says VREF to one, feedback VA is gonna be zero. So if VA starts out as more zero, it's gonna reinforce VREF being the opposite, and that's gonna be feedback. And that's basically it. That is basically the intuition. Um, and I keep using that word, but of how this thing is working. Of course, it's analog, so it's these things that I'm presenting is not gonna be exactly one or zero. It's gonna be slight voltages over time until it is reinforced to either be. When I say one and zero, of course, once again, I'm talking about one as VDD versus zero as ground. Of course, voltages are relative. So I'm gonna kind of draw this out more intuitively. Um, so we have VDD, or maybe it's better to draw it like this. We have VA, you have VB. Oops. So these are just general lines. Um, usually we'd have an enable to turn it on, but we'll just kind of ignore that. We just kind of have an inverter here and this being inverted there. So what we're really doing is using a race condition to our advantage. We're basically saying if you're whichever one of you is a stronger one, sending a stronger input to your corresponding gate, you're gonna win and um, set the other one to the opposite, and that's gonna be the feedback loop. Um, so yeah, that's pretty much it. There's not much to it. That is, um, that's what's happening here, really. Yeah, I guess we can draw in VDD. Um, Actually, it's okay. This is not exactly um, this is not exactly the more technical diagram that we had here. But that is basically how a sense amplifier works. I hope this was helpful. We'll see if I post this or not. Maybe I'll update it later. But yeah. All right, guys. Have or everyone have a good day and hope you learned something. Subscribe to my channel for more digital logic stuff and comment if this was helpful and what other topics you would like me to cover. So, anyways, thank you guys. Have a good one.